called Sustainable Marine Methanol, and it's a sister project to the GreenPilot project, if you will, a parallel project. We've got quite a few of the same partners, plus some more partners working in Summit, and we're funded, you can see at the top, by Swedish Maritime Administration and the University of Götaland, the Western Gothenburg region, Methanol Institute, and Oil Tanking, who are helping out the Finnish partner in the project. Otherwise, it's a Swedish group carrying out the project. I don't have the slide So all let's go through today is some background to the project. You might have heard some of this already this morning, so I'll try to go fast over that. The objectives, and then talk about some of the different components in the project, the main areas, the engine research, design and safety that Joachim will explain, market research work that's underway, and work into sustainable methanol supply chain, and summarize. I don't know if you've seen this, an outline, an overview of all the marine methanol research projects. You got this morning, something very similar. Okay, so the Method and, up to Method looking at bigger vessels, and some of the GreenPilot looking at solutions for smaller vessels. And the drivers for methanol fuel development for smaller vessels, well, as probably was said this morning, and the problem with the larger vessels as well. There are no commercially available engines in the small engine segment up to 1,200 kilowatt range. There has been some development for the Germanic for that retrofit solution, and then also with the MAN engine for the chemical tankers, but there's nothing done except for what we've heard from GreenPilot for the smaller vessels and engines, and Summit is also looking at that. And also, smaller passenger vessels are also operating in populated areas where things like particulate emissions are really important locally, and so it's important, even though there aren't so much regulations right now on the international level for the larger ships and particulates in regional areas and cities where these smaller vessels are operating. There are air pollution concerns and issues, and methanol is really good for reducing particulates. It's so clean burning. And as well, there are different challenges and opportunities for methanol solutions for smaller vessels that should be looked at in projects like Summit and GreenPilot. So the objectives of Summit were to test and evaluate different methanol combustion techniques for smaller engines. We have two partners looking at that, and to develop the case study design for methanol conversion of a Swedish road ferry, and investigate the market for smaller vessels in northwestern Europe, identify the numbers of vessels and where they are also, which will help to look at possible renewable methanol supply chains and identify areas and potential buyers. And overall contribute to a solution to reduce emissions and the carbon footprint of smaller vessels. The engine testing, two partners are doing lab work on this. VTT, Technical Research Center of Finland, has looked at the solution of using an additized ignition enhancer for the fuel, and so it's what is done now, what Scania does for the ED95, using barium to enhance ignition. So they've looked at doing that with methanol, and they looked at some solubilities of different blends of different ignition enhancers, and they did some combustion chamber testing and have just finished up their engine testing work in their lab engine, the Scania engine. And here they said that the combustion was very good with the MD95, and here they've been showing the NOx emissions. So the MD1 is the similar, comparable to the RE, the reference ethanol 95, so the buried, and it's showing that the methanol, using methanol with the same ignition enhancer is giving even lower NOx emissions, and that they found no significant formaldehyde emissions for this concept, and they're looking further and now analyzing their particulate results for some of the additive candidates that were adding more lubricity. So they're going to have more reports on this later in the project. The Summit project finishes up at the end of 2017, so there'll be more reports and official results in. And they found this very promising concept for further development. The other partner doing engine work and testing in the lab for this is Mund, and we heard Martin Tenaire earlier. And so far they've done tests with thesis work, Lee Bjornestrand, who's looked at ignition, direct ignition spark combustion, and they found indicated gross efficiency of 54%. And further testing that they're doing in the summer and fall will be on port ignition with the glow plug concept. I'm not sure if Martin's still here, but I don't think he has any more to add. The case study is for the Swedish boat ferry, the MS Jupiter, 86-meter length and capacity of 399 passengers, and is currently running on diesel fuel. And the design work is now going to be explained by Joachim. And further after that, I wanted to say we're going to also do cost comparison and emission reductions for this vessel, comparing methanol with the current operation.
Thank you. The design of the methanol systems for this road ferry is very similar to the pilot boat, actually. We also have the same engine size and very much the same. So I'm not going to get into details of the background as I did with the GreenPilot project. But we also have the same set of rules basically to relate to. We have the national statutes from the Swedish Transport Agency, and we're also looking at the classification rules and the IGF code as reference. The difference, of course, is that they have a large number of passengers on the road ferry, in contrast to a few crew members on the pilot boat. And the baseline is, of course, the same. The methanol systems must be at least as safe as a conventional system. And quite similar. And also going, but I'm going to go through the same thing. The fuel system, the tank. We also have tank inertion on this size as well. The gas detection and fire detection and suppression. So first of all, looking at the what the ferry actually looks like. So here we have the dominating thing, of course, is the large cargo deck with most of the passenger cars. Below that, we have a different number of we have a tank room, different tank room and engine room in each side. So it's double symmetrical, almost. So these are the tank rooms today. I'll say almost double symmetrical. We have the tank slightly to the port side of the vessel from the center line there. But both tank rooms are similar. We will, in the proposed design, we have converted one of these tank rooms to methanol and used the other ones for diesel. So we still have the diesel capacity on board. And today there are two 28 cubic meters tanks. During usual operations, there are the full capacity is never used, but they're still available. And there are the tanks looking from above. And there we have the two engine rooms, also very similar. The aft one, this one, also have a burner to produce heat, but that's more or less the only difference. And they are not connected in any way. They are two separate systems, each taking fuel from one tank each, and then there's a transfer system between the tanks. But there's no transfer of power from one side to the other. And today the main engines are four Volvo Penta engines, 300 kilowatts. Usually run on quite low load during operations. Coming to what we have done for the methanol conversion, the fuel tank, of course, is quite a big part. We need to make it a little bit smaller to fit all the different other systems. If we do that by rebuilding of the tank or installing a new tank, is still up for debate. But an alternative is, as mentioned before, to have some sort of coating in the existing tank. But we need to take care of the properties of methanol. But what we're going to do is we build a new bulkhead, a gas-tight bulkhead, to separate the methanol tank room from the rest of the ship, because this is the escapeway from the engine room. There is a secondary escapeway as well, but this is the main pathway. We don't want to pass through a methanol tank room coming out from the engine room in case of anything happening. And we also have fire insulation on the bulkheads beside here. We have a new ventilation system, so I have a separate ventilation system for this tank room. So we have an inlet and an outlet on the other side that's powered as well. Also a new methanol drain tank. And inside the tank room we also have the fuel pumps and fuel filters and that part of the equipment, in contrast to the pump chest that we have in the pilot boat. But this is of course safe to the rest of the ship. As Daniel mentioned, we don't have an airlock in this compartment, which is a requirement for in the current IGF code for the larger ships, that we need to pass through one door and then pass through another door to get into the methanol pump room. But we don't really think that is possible here, and we don't really see that as a requirement from a safety point of view. Inside the methanol tank we have nitrogen injection, as previous, and then we're coming here some pipes from the above. The methanol tank is 25 cubic meters. We have a 150 millibar overpressure, as in the previous design, with a PV valve on the ventilation. This is the ventilation. On the ventilation pipe there is also a safety overflow system with a burst disc, and that's draining to overboard, because methanol is not hazardous to environment. In case of danger, it is safe to dump it overboard. It's at least from our point of view. There's also there. Here you can also see the bunker connections in this pipe here going up to deck. And there, it's a similar connection as on the pilot boat, the dry disconnect coupling. There's those. Looking at on deck, the bunkering operation, what we imagine is to have a truck come on board, park close to the bunker connections, and just fill up the tank. During bunkering operations, no passengers are on board, and it's safe. And this is exactly the same way as they're bunkering diesel today. Then the connection is over there, but it's probably the same. Now you can see it right above the tank room. We have the same double-walled piping inside the engine room. In this case, we don't have any equipment other than that inside the engine room. No pump chest or no part of that. And the modifications is mainly the modifications to the engine, or the new engines that should be installed. We have the same gas detection in the tank room and in the engine room, as well as on the engine. This is something that need to further evaluation where to put the actual gas detections. But inside the engine room there is really nowhere except for the engines where any leakage can occur, because the piping is double walled, and also there is no connections. We have the same alarm levels at 15% LEL and 30%. It's a gas detection. It's a gas fire extinguishing system on board we propose to use. In this case it's an Inogen system, not a carbon dioxide, but it works similar. Today it covers only the engine room, but it should cover also the methanol tank room. And then we need a deck wash system. That's a system to put water on the car deck, because that's not fire insulated today. When it comes to fire detection, heat detectors is the use. In this occasion, IR detection of methanol fires should also be a possibility, because this is a larger engine room, so it's not as easy to have heat detectors. At least we don't believe so. And visual FLIR heat detecting cameras could also be a solution. I think that was more or less what I had on the design, because it's very similar. There's a diesel connection, there's a tank room, that's the engine room. CO2 bottles and nitrogen room should be here on deck. And on the 25 cubic meter tank we get about 1 week of operation on methanol, when calculating from the current diesel consumption. So I hand this back to you.
Thank you. also about this design doing hazard identification process as well, just providing input to the design. And as well for this design, we'll be looking at, now the design's done for the case study, to look at costs as well. Not just costs of the conversion, but cost savings if you're using methanol, for example, and the vessel currently has particle filters. So all the operational cost savings that could be expected. And the market analysis is looking not just at one vessel, but trying to identify the whole potential in this Northern European sulfur emission control area for the engines in the particular size range that we're interested in the project. So it's broken into two categories. The first, the engine size having an automotive equivalent, and the second, the larger engines, marine engines. And it's using AIS data, automatic identification system records, to determine the number of vessels, but also some modeling and other input, because the AIS data doesn't have engine information for all of those vessels, only about a third of them. Then that information will be used together with some ship emissions, engine emission information coming out of the project to get some indication of some of the potential emissions benefits for converting larger fleets in an area to methanol operation, and and also the potential cost. For which ships would it be? Would there be a business case for converting to methanol? And the final work is looking at supply chains. Okay, here we've just shown biomass, which I just learned from Daniel is maybe not the most efficient from a land area perspective, but we're also, which is not shown on the slide here, we're also looking at things like, in this study, looking at biogas, for example, to make methanol, and looking at if we can identify areas and volumes of methanol through looking at the AIS data, and where could a good potential be for siting a small methanol production facility, for example. So this information could be useful on the methanol production side. And there is quite a lot of potential for smaller methanol production. I was at the methanol policy forum in Washington and learned about, container-sized facilities that could take biogas and produce methanol. And if you're looking at smaller vessels spread out over a larger area, maybe you want to have more localized production of methanol. That might make sense. So it's a theoretical study looking at these different issues. So to summarize what we found so far, that it's very good potential for smaller vessels, and the conversion of smaller vessels is feasible. Of course, we've seen that with GreenPilot. Supply of sustainable methanol is really important, though, and some of the smaller vessel users and the Swedish boat ferries, for example, will be bringing in, maybe meeting tougher national standards for CO2 regulations. So they're setting their own targets, and maybe municipalities as well. So things can move faster for the smaller vessel side in municipal and national vessels if targets are set for the whole overall transport system, and shipping is supposed to be part of contributing there. So it's really good potential. And finally, we're going to have some sort of final project workshop presentation at the end of 2017 when Summit is finishing up. So we hope to see lots of you there.
Thank you. Do we have any questions for Johan and Joachim? None. We are keen to see the results. Then I would like to welcome up, because what is left now is that we will have a short panel. And the panel will consist of Fredrik Almlöv, which you have not seen before. Fredrik, please come down.
Okay.
And Fredrik, he is a technical manager of ferry operations at the Swedish Transport and Administration. We will also have Bengt from